Hi, everyone, and welcome to this afternoon session for e-drilling live webinar presentation. Thank you all very much for registering and joining us today. Hopefully, you should be able to both hear and see us clearly. If not, please let us know. So I can start by introducing myself. My name is Alina Sundasklev, and I will be taking you through the next 30 minutes of this webinar presentation on prediction of stuck pipe incidents using models powered by deep learning and machine learning. And today I'm joined by my colleague Anvisha, who will be presenting the subject on behalf of eDrilling. So let me introduce you to Anvisha. No worries, Anvisha, take your time with the presentation.
Sorry.
No worries. There we go. So maybe if you can move to the next slide, Anvisha. There we go. Perfect. We're on a roll. So Anvisha is our machine learning specialist in e-drilling, and she has a master's in computing from the National University of Singapore. And her background is mainly in AI, data science, machine learning, and deep learning. So welcome, Anvisha. Thank you very much for joining us and presenting this very exciting subject. So before we get started, let me just give you a quick introduction of the agenda for this webinar. This is a fairly short webinar for about 30 minutes. However, we have dedicated a couple of minutes at the end of the session to address any questions that you would have. So Anvisha is going to start by introducing or giving you an overview of artificial intelligence by defining AI and the difference between AI, machine learning, and deep learning. She's then going to do a deep dive into how data is gathered, cleaned, and labeled by showing you an overview of the models, discussing then the results and the advantages of the models. And as mentioned, we also will leave a couple of minutes left at the end of this webinar for a Q&A. If you look to your right, there is a chat section. You can use that and feel free to use it for any questions that you would have during the webinar, but you can also message me privately and I'll leave my icon in the chat shortly. By clicking on that icon, you can send me private messages if you wish to stay anonymous as well. Yes, I think that's enough for the introduction. So Anvisha, without further ado, the word is yours.
Hi, I'm Anvisha and I'll be taking you through our webinar today. So I thought the first topic we should discuss is talking about what artificial intelligence is and giving everyone a brief overview of what it entails. So you've probably heard all of these words since they're quite popular and being thrown around everywhere. So what are they? Artificial intelligence basically refers to the category of all programs and algorithms that enable programs to emulate human intelligence. So they include machine learning algorithms plus other algorithms like, say, genetic algorithms, etc. Now, machine learning is a subset of artificial intelligence. And this specifically refers to the set of programs that learn from the data. Instead of explicitly coding thresholds, etc., you feed the algorithm data and it learns based on the data you have provided. Now, another very popular word is deep learning. So, what is deep learning? Again, it's a subset of machine learning and it uses an architecture called a neural network. So, a neural network usually has an input layer, an output layer, and multiple hidden layers. So, if a neural network has more than one hidden layer, it is called a deep neural network. And use of such an architecture for your machine learning problems is called a deep learning approach for machine learning. Now, coming to the types of algorithms in machine learning, you have supervised and unsupervised algorithms. Unsupervised algorithms usually refer to the set of algorithms where you do not train the model beforehand or teach the model beforehand. You provide the model with data, and the model itself looks through the data and tries to find patterns in this data. So, examples of unsupervised learning algorithms would be clustering, where you try to cluster and find groups that have similarities amongst themselves. Now, unsupervised learning is the more popular form of machine learning that is used, and it basically means learning from the data. So, you provide the model with labeled data that it can learn from, which we call training the model, and then it uses what it's learned to make predictions or perform tasks on data which it hasn't seen before. And again, unsupervised algorithms are broadly classified into classification and regression. Classification would be when you are trying to categorize different sets of data into common categories. Say you have cats and dogs, and you're trying to use images of cats and dogs, and you would use a classification algorithm to identify which one is a picture of a cat versus a dog, a very basic example. And coming to regression, you try to predict values given certain parameters into the future. So say stock prices, your weather, prices of a house, these all would fall under regression algorithms. Now, what are the benefits and uses of artificial intelligence? As you would know, artificial intelligence is pretty much used in several applications throughout. It's used on our phones, lots of household devices such as smart devices like Alexa, Google Home use it, and it is broadly used in these types of ways. One is for computer vision, so you deal with image based data. Second one is natural language processing or NLP, which deals with text based data. Time series analysis deals with usually structured data, which you try to predict into the future. So they definitely have timestamps associated with them, and the values of the variables would change with time. And another thing artificial intelligence is largely used for is predictive maintenance, where you try to figure out whether a certain part or a certain device is going to malfunction, and if so, when, and you take the necessary steps to replace the part or make the fixes so that you can avoid the part failing and then you losing on your productive time. And in the drilling sphere, I think time series analysis and predictive maintenance are two big areas of interest where we do use artificial intelligence. Now, I will talk about our model and what our aim is and how we do it. So, the basic aim of our model right now is to predict the occurrence of a stuck pipe situation prior to it actually happening so that we can avoid it. And now I'm going to discuss how the model works. There are four major steps that happen one after the other in our model, and the final outcome is the results. So the first step is the data cleaning and labeling. This is where you collect data from several wells, which we have done. We clean this data, we select which parameters are the most important to us with regards to what we are trying to predict. So in this case, since we're trying to predict stuck pipe situations, we go through the set of attributes that we have and use certain algorithms to determine what features have the maximum impact on detecting a stuck pipe situation. And we also label the collected logs, and this is done by drilling experts in the field. And there are two reasons for labeling the logs. One is so that you have data to compare your results with, which has been accurately labeled by the drilling experts. And the second reason we label the logs is for training purposes. So when you train our classification model, we use this labeled data so that the model can learn from it. Now, the second step of our model is our deep neural network, which performs the time series prediction. For this, we use an architecture called a recurrent neural network, which is very good at handling time series data. And what we do is that we feed these 12 the values of the 12 parameters into the model, and the model predicts the values into the future. And the model is designed in such a way such that it predicts the values of the 12 features in parallel. So you basically have 12 deep neural networks running simultaneously. Now you get, as a result of this step, a data set containing the predicted values of the 12 features. This data set becomes the input for the third step of our model, which is the classification model. The classification model uses a random forest classifier, and this model has been pre-trained. After that, it is introduced to the data set from the previous step, and it makes a prediction on that data and determines whether it thinks that it is going to encounter a stuck situation or not. So one thing I'd like to mention about the training process of the classification model is balancing our data set. Because in drilling, the number of cases of stuck situations are way fewer than the number of cases where normal well operations happen. If you train your model without balancing the data set, the model would predict with high probability that you would not get stuck. Because say you trained your model with 100 wells and 99 of them didn't have a stuck case and only one well did. So the model would be likely to say, okay, it's not stuck, because based on the training data, it's learned that if you predict that it's not going to get stuck, you have a higher likelihood of being right. But this decreases the efficiency of the model because it is unable to actually detect true stuck situations. So for our software, we made sure to balance the data set while training it so that this does not happen. And lastly are the results. So from the classification model, we obtain labels identifying whether it's stuck or not. And then we take these results, and to make sure that the model is performing well, we compare it to the uh, labeled by the drilling expert, which I talked about in the first step. And it is important to note that the parameters we use for checking to make sure that the model is performing well is not only accuracy, but there are other parameters called precision and recall. So this would make sure that your false positive and false negatives are being counted in the assessment of your model, and you're not getting a high accuracy only, but actually a good model which can avoid false positives and false negatives. That is cases where it isn't stuck, but the model predicts it as stuck, or it is not stuck and the model says it is stuck. So let's move on to the next portion of the webinar, which is the discussion of the results. Before discussing specific examples from wells that we have tested on, I'd like to go over a summary of the results that we have obtained, and these are the main points that I'd like to highlight. Firstly, the model is able to forewarn of a stuck pipe situation occurring with high accuracy. Secondly, the model is able to make the predictions in line with what the drilling experts say, and sometimes even before the drilling experts notice any warning signs. Since it is a machine learning model, it is able to update and learn with changing trends. So you do not need to manually go and reconfigure the model every time. And it is also important to mention the model is also able to correctly detect not stuck situation in wells where there aren't any such incidents. And I believe this is important because you wouldn't want a model constantly telling you that you are going to encounter a stuck pipe situation when you actually won't. So we tested for this scenario as well. And now we can go on to looking at a few of the examples. So this is a sample well which did have a stuck pipe situation, and as you can see, the accuracy, precision and recall are all quite high, which means that the model was able to make predictions that align with what the drilling expert said, and it did so with high accuracy. And this is a graphical representation of the result. The part highlighted in red is the part that the model predicted, and the part highlighted in blue is what the drilling expert said. And as you can see in these two plots, the model either gives a warning prior to the what the drilling experts have said, or it agrees with what the drilling experts have said. Both are quite good signs. Now moving on to the next example, this is another well which did have a stuck pipe situation, and as you can see, again the accuracy, precision and recall are quite high. Obviously for each well it can't have the same accuracy, precision and recall. Also because the model sometimes gives warnings prior to what the drilling experts see, it might not always match the exact time intervals that the drilling experts have mentioned, but the model is doing as good or sometimes a better job. And again, you can see the plot from this model, and you can again see that the red highlight happens before the blue part. Now, finally coming to the third and final example, which is a well where there was no stuck pipe situation. And as you can see, the model correctly said that there was no stuck pipe situation, which, as I explained before, we believe is equally important so that you don't have a lot of false warnings. And here is the plot for that well, and you can see there are no highlighted portions since there was no stuck pipe situations observed in this data set. And now coming to the final portion of our webinar, which is the advantages of the model. So the biggest advantage of the model is because it runs on data and it is able to learn from the data. It has the ability to adapt and update according to changing trends without, again, needing to be tweaked or changed by any external input. Secondly, since it's a model which is run by AI, it runs constantly and can monitor 24/7. Thirdly, it can contribute to greener drilling by reducing the amount of emissions, by making the process more efficient and safer. It helps reduce costs because it can largely bring down your non-productive time. And it is also a step towards automatic drilling control. And that's quite an interesting thing to look into. So these are some of the advantages that you would get from this software. And now, if you have any questions, please feel free to ask.
Thank you very much, Alicia. That's a quick and efficient presentation on deep learning and machine learning for stuck pipe incidents. So I see we have some questions that turned up in the public chat. Again, everyone, if you still have some questions, we will be spending the next 10 minutes to address any questions that you would have on this subject. I'm going to start with the private chat first, and then I'll move on to the public chat afterwards, and hopefully we should have enough time to address all of them. I have one attendee here asking about the development of the machine learning. So the question is, are you planning to develop other machine learning algorithms which can also help reduce risks in drilling operations?
Yes, the plan is to eventually develop other machine learning models that can help reduce risk. Stuck pipe situations were the first thing we decided to tackle, but eventually we will move ahead with building more models to address different problems in drilling.
Perfect. Thank you for clarifying. Also, another question here, you might have touched on this already, but is the model series supervised or unsupervised?
So the time series model which we use is supervised. So how it works is, say it takes the first 1 hour or 2 hours of data from the start of the drilling process to learn, and then it learns on the go. So as and when new data comes, it keeps updating and giving the responses, and it learns from what new data is coming in.
Great. There are a lot of good questions here, Anisha. So I'm trying just to take this in a specific order. Let's see. One attendee is asking, how long prior to a stuck pipe situation can machine learning detect this event?
So we have left that changeable. So you can technically choose how far back in time you want to look and how far ahead you would like to predict. But for the purposes of this presentation and the results that I shared, we looked back 1 hour in time and predicted 30 minutes into the future. And the reason why we chose to do this is because we talked to different people, drilling operators, drilling experts, and they thought that this would be a sufficient amount of time to make the necessary changes so that we could avert such a situation from happening.
Right. I also have a question here on the data cleaning and labeling, which you mentioned during your model overview. The attendee is asking, You mentioned data cleaning and labeling. Are there any specific data requirements when collecting data from wells?
So these are one of the major challenges you face when dealing with drilling operations is getting good, clean data. So different drilling operators use and collect different parameters. These parameters are addressed by different names based on who's drilling it, and also the drilling operators chooses which parameters they are collecting, so it is not uniform throughout. So when you are feeding the data into the model, you need to make sure it is uniform. So taking all the raw data and making sure that you have the same parameters and the same values and that they're mapped correctly so that you're reading the correct attributes is a very important process and also a time consuming process, but it has a significant impact on how well the model performs, because if your data is not of good quality, then your model's predictions would not be of good quality.
That's good you clarify, Anisha. I see in the public chat actually that this question was also addressed, asking if the data cleaning is automatic or manual, but I believe you highlighted now that this is a manual process. Maybe you can just clarify one more time.
So we have scripts which run the data, like which collect the raw data and clean it. So now it is an automatic process, but the initial setup of that script to make sure that it happens correctly took time.
Okay, perfect. Thank you. Another question here, it's a bit of a commercial question, so maybe I can help address that. The question is, e-drilling already has an effective AI solution in avoiding non-productive time. How is development related to this? That's a great question. So let me try to keep that as clear and crisp as possible. So our current real-time software solution is using model-based reasoning in AI. And what this does, it compares the observed or the calculated data with the physical model or the physical well. So any of our software users are then being provided with diagnostics that are triggered when there's any deviation between the models. And we do this, or the objective with this is to avoid any risks, any incidents, but also the non-productive time. And it also includes features such as the detection of pack-off, and as Anvisha also has highlighted in this presentation, the prediction of any type of stuck pipe situation. And this technology we have developed and deployed to multiple wells globally as well. So just to wrap up that question on the commercial bit, the machine learning algorithms presented here will enhance this type of solution. This is also what we will continue to focus on, specifically when looking at stuck pipe situations or prediction of stuck pipe incidents. So I hope that clarifies your question in terms of development. Another question here, Anvisha, is how long it took you to develop today's model?
So we have been working on this model for approximately a year now. As I mentioned before, a large part of it was setting up a pipeline for data collection, cleaning, and labeling. And then we developed the models, and then there was the whole testing phase. So, overall, with all of these things taken into consideration, we've been working on this for about a year.
About a year, okay. Also, is this model applicable for drilling BHA?
It should be, though we haven't tested on that yet.
Okay.
But I can
Actually,
look into it and get back to you.
Sure, absolutely. So if we feel like we want to elaborate on these points as well, we will reach out to you individually after this presentation. So for sure, we can do that. A question regarding how this contributes to greener drilling, actually. Anvisha, you say that machine learning can contribute to greener or more sustainable drilling. How can you be measuring this?
So there are no specific parameters or numbers that you can use, but in general, by using machine learning models, you can avoid such situations from taking place, and that itself would make the drilling process faster and save and cut down on a lot of emissions. Also, when you do encounter a stuck pipe situation, there's a lot of effort and energy wasted on clearing it up or re-diverting the whole route of the drilling so that you can avoid the stuck pipe situation. So that adds to time, that adds to more energy. And just by avoiding all of that, you'd be cutting down largely on the emissions, and that would definitely make the drilling process greener than what it is right now.
Absolutely, absolutely. I'm moving on to the public chat now. Thank you everyone for engaging in this public chat. We appreciate any questions that you have on this subject. These might be a bit specific, but we'll give it a try. One of the questions is why do you have an ANN and then you have a 3 classifier on top of that? So I guess you're referring to one of the first slides to Anvisha here.
Yeah, so the logic was that rather than having a time series value directly predict a label, we thought and tested it. We decided that it would be better that you have the ANN predict the values of the independent features into the future, and then take those predicted values and then feed it through a classifier so that it can predict the label. Say, for example, if I want to predict the weather next week and I have parameters such as humidity, temperature, precipitation, etc., etc., and I have data from the past 2 weeks and I want to predict 1 week into the future. So instead of just directly being able to predict whether it's sunny, cloudy, or rainy, I predict the values of what the humidity, precipitation, or and other parameters would be 1 week into the future, and then I classify it with a trained model which has seen previous data sets, and it we largely saw that that improved the accuracy of the model and gave much better results.
Perfect. Thank you, Anisha. We still have some great questions. We have about a minute to 2 left, a minute before we wrap up. So one attendee here is asking if we also use lithology data in your model.
No, we do not use lithology data because, again, as I said, one of the main challenges with drilling is data collection. And since you need historical data to train your models and test your models, it's been a challenge finding lithology data for historical wells. So we decided to avoid that, because if you trained a model where you had lithology data available for certain wells and you didn't have for others, it wouldn't scale well and you wouldn't be able to apply the model to a wider array of wells because you might not have access to that data in those cases.
Okay. I see we have about a minute left, so I'll take the last question here before we wrap up. Are physical models used in the process?
Could you elaborate on that?
Yeah, so it's a very specific question. Maybe I can move on. If the model can predict which kind of stuck pipe event is going to happen.
No, the model does not try to predict specific subcategories of stuck pipe events. And again, this goes back to the data collection. You would need a large number of wells of each specific stuck pipe case to train a model well enough to be able to deal with such a thing. And it is very hard to come by that sort of data, and also so many wells where you've had specific types of stuck pipe situations. So like say 10 of each type which have encountered the same type of stuck pipe situation. So rather than that, we've kept it generic to predicting stuck pipe versus no stuck pipe.
Right. We can definitely get back to you on this question and elaborate further after this webinar. I see we're running out of time, so we do have to wrap up. If we weren't able to address your questions, we will reach out to you individually after this broadcast. And please, if you still have any questions for us after this webinar, feel free to reach out. You will also receive a recording of this webinar a couple of hours after this broadcast has ended. So thank you everyone for attending today. Thank you for all the great questions you've provided as well. Thank you, Anvisha, for this presentation. Enjoy the rest of your day, everyone.
Thank you so much.
Thank you all. Bye-bye.